Back in 2015, this one paper came out with an idea, and it was so simple, but wow, was it powerful. It pretty much changed the entire game for artificial intelligence. We're talking about a paper that solved this massive problem, a real head scratcher for all the top minds, and it just blew the doors wide open for the kind of super deep AI models that we use for everything today. But, okay, before we get to the brilliant solution, you've got to understand the problem they were up against, right? So picture this. It's the mid-2010s, and AI researchers are just stuck. They're hitting a wall. The thinking was pretty straightforward. If we make our neural networks deeper, add more and more layers, they should get smarter. They should be able to learn way more complex stuff. It makes perfect sense. Except when they actually tried to do it, something really, really weird started happening. And this chart right here, it just lays out the whole paradox perfectly. You've got a 20-layer network, and hey, it's doing pretty well, right? Low error rate, not bad. But then they build this much deeper 56-layer network, and get this, its error rate was actually higher. I mean, the deeper network was doing worse. And not just on new stuff, it was doing worse on the exact same data it was trained on. It made zero sense. So yeah, this wasn't some random bug or a one-time fluke, no way. This was a massive, fundamental roadblock. And it got a name, the degradation problem. And honestly, it was holding back the entire field of deep learning. Okay, so here's the key thing to wrap your head around. Once these plain networks hit a certain number of layers, adding more wasn't just, giving you less bang for your buck. It was actively hurting the performance. The training error, how well the model did on its own practice questions, basically, was going up. It was the complete opposite of what everyone expected. And the authors of the ResNet paper, they really hit the nail on the head here. They said, look, in theory, a deeper model should never be worse than a shallower one. Why? Because worst case scenario, the extra layers could just learn to do, well, nothing. Just pass the information straight through, like a copycat. But the fact that these networks couldn't even learn that simple do-nothing task, that was the big red flag. It meant the whole learning process, the optimization was just fundamentally broken for these really deep networks. And this is where the magic happens. Staring this super frustrating problem right in the face, the researchers at Microsoft had their aha moment, and they came up with a solution that, looking back on it now, is just breathtakingly elegant. The big idea was called residual learning. And honestly, the best way to think about it is like this. Imagine you're an artist. What's harder, drawing a masterpiece from a completely blank canvas or taking a really good sketch and just, making a few tweaks to perfect it? The second one, right? So instead of forcing the network to learn the whole complicated picture from scratch, they completely changed the game. They said, hey, network, don't worry about the whole thing. Just learn the changes, the residuals, the little touch-ups you need to make. So how did they pull this off? How do you actually teach a network to just learn the change? Well, the answer was shockingly simple. They created a shortcut. Okay, check this out. This is the heart of ResNet, the residual block. It works like this. An input comes in, right? Now, instead of just forcing it through these processing layers here, the signal gets to split. Part of it goes the normal route, but the other part gets to take this express lane, a shortcut that just completely bypasses all that processing. Then, at the very end, the original untouched signal from the shortcut gets added right back to the processed one, simple as that. And this just makes the difference crystal clear. The old way, the plain nets, they were forcing every layer to learn the whole complicated transformation from scratch. But the new ResNet way, it made the job so much easier. Now the layers only had to focus on learning the tiny correction needed, because the main signal was already guaranteed to get through thanks to that shortcut. So if a couple of layers weren't really helping, the network could just learn to make their output 0, and poof, the original signal passes right through. Just like that, the degradation problem was gone. All right, so the idea is beautiful on paper, right? Super elegant. But the million-dollar question is, did it actually work in practice? Oh, it worked. And the results weren't just good, they were absolutely world-changing. Okay, so remember that first chart that was so confusing? The one where deeper meant worse? Well, look at this. With these new residual networks, the whole paradox just vanishes. In fact, it's the exact opposite. A deeper 34-layer ResNet is now way better than the shallower 18-layer one. For the first time ever, researchers had a reliable way to get better results just by adding more layers. Deeper finally meant better. And you think they stopped at 34 layers?
Heck no. They just went for it. They pushed this thing to the absolute limit, creating a network that was, get this, 152 layers deep. To put that in perspective, that was a staggering 8 times deeper than the best models of the day, like VGGNet. So, they took this beast of a model to the ImageNet Challenge, which is like the World Cup for computer vision, and it absolutely crushed it. Their model hit a top 5 error rate of just 3.57%. That means out of 5 guesses, it got the right answer over 96% of the time. What's crazy is that's actually better than human-level performance on that same test.
And yeah, that performance wasn't just good enough for a pat on the back, it won them first place. A clean, decisive victory in the biggest computer vision competition on the planet in 2015. And this table really puts that win into perspective. I mean, look at these numbers. ResNet didn't just sneak by the competition, it completely blew past all the old champions. We're talking about almost cutting the error rate in half compared to the winners from just the year before. This wasn't just a step forward, it was a massive leap. So, winning a big competition? That's awesome. But the real story here, the lasting impact of this paper, goes so much deeper. It wasn't just about one win. It fundamentally, and I mean permanently, changed the playbook for how we all build AI systems. So let's just recap what this thing did. First, it completely solves that degradation problem, which finally meant we could train networks that were insanely deep. Hundreds, even thousands of layers. That architecture, it pretty much became the blueprint, the backbone for almost every big breakthrough in computer vision that came after it. Think about self-driving cars, medical image analysis, all that stuff. And it's wild to think that it all traces back to one incredibly simple, powerful idea. Just add a shortcut. You know, it's such a great lesson about innovation, isn't it? The answer to one of the gnarliest problems in AI wasn't some super complicated new formula. It was actually the opposite. It was about simplifying, finding a smarter, more elegant way for information to get where it needed to go. It really makes you wonder, right? What's the next simple shortcut out there that's just waiting to change everything all over again?